Okay, let's try this problem. We've got a automobile that is on a turn and it doubles its speed. How much additional frictional force must the tires provide if the car safely makes it around the curve? So there's a whole bunch of assumptions in this particular question. Essentially, it's talking about you've got a car that is on some sort of circular track, and we have to, in order to solve this, we pretty much have to assume that it is uniform circular motion. There's some radius to this track. There's a velocity to the car, and the velocity, of course, is perpendicular to the radius, and that is equal to v. And yeah, anyway, I said uniform circular motion. We can't really solve this problem if it's something other than uniform circular motion. So it's going to some kind of turn, and let's presume that it's a circular turn and that the velocity doesn't change. So those that's a big, I guess we'll call this assumption. Okay. Now, what's the frictional force? Well, we know that in uniform circular motion that because of this changing velocity, we will have an acceleration pointing towards the center. It's centripetal acceleration. Actually, it's goofy that I drew it like that. So in this location, let me use a different color, the acceleration is pointing directly towards, it's pointing directly in this direction. There's a centripetal acceleration. So on a free body diagram for this car, what I would do is I would draw something like this. So this dot represents the car, and there is some frictional force that is in this direction, and this frictional force is the thing that's keeping the car from flying off tangentially. By the way, I should mention that this is really a top view of the whole situation. So we're looking at the top. This guy right here is the car. Here's the velocity. The acceleration we know is toward the very center of the radius of the track. And if I were to kind of draw a free body diagram over here of the situation, this dot represents the car, and there is a force of friction in this direction. And we know that that frictional force is equal to the mass times the centripetal acceleration. So here we've got the situation where the first frictional force must equal the mass times the centripetal acceleration 1, and we know that that's equal to the v1 squared over r times the mass, or m. This is actually, I didn't do that very well. This term, the acceleration, is v squared over r, where the r is just the radius, and the v1 is the velocity. So now, if we take the second scenario, we have that second force is equal to the same mass times the second acceleration, a centripetal 2, which is equal to v2 squared over r times m. And what we're told in the problem is that we actually double the speed. So we know that v2 is equal to 2v1. Therefore, if we just substitute this in, if we substitute that value into here, we see that what we get is the mass cancels. So what I'm doing is looking at this equation, this top equation over the bottom equation. So the mass cancels. I'll do that over here. Mass cancels. The r's cancel. And then we have v1 squared over v2 squared. Let me write that down here. F1 over F2 is v1 squared over 2v1 squared equals v1 squared over 4v1 squared. So these guys cancel, and we're left with this relationship that f1 equals over f2 equals 1/4, or in other words, therefore 4f1 equals f2. So if we in fact double the velocity, what we do, because of the velocity, the acceleration is related to the velocity squared. Here, acceleration is related to velocity squared. We double the velocity and we multiply the force required by a factor of 4.